Hey, Elliot, how's it going?
It's going fine.
Good. Neo, how are you? Neo, can you hear me?
Oh yeah. Yeah, I had my other headphones plugged in, so
Oh.
it didn't work. I had to change that.
How's your automated system going?
It works for all my classes now, at least.
That's good.
Yeah. Um, it's kind of it like joins 5 minutes early, so and then I just need to make sure to come back and click like join with video.
Neo. Hey, Steven. Hey, Megan, how are you?
I'm good.
Good. Who else just came in? Aro, is that how you say it?
Yeah,
How are you doing?
pretty good. How are you?
Pretty good. It's Friday, that's a good thing. Philip, I'm assuming that means you're in the drum line.
Yes.
What's happening with band right now?
We just did band camp, which was online, and now we're doing the same thing, I guess, but in school.
How did you do it online?
Um, it's basically like in your section, one person plays unmuted and everyone else plays along muted.
Okay.
But the problem is like the teacher can't hear people playing,
Right.
so it's kind of flawed.
Sure. Yeah. Yeah. I guess if you all did it at the same time, it would be way worse, though, huh?
Yeah, you bet.
Looks like we are mostly here. All right, I guess we will go ahead and get started. We're missing a couple people, but maybe they will show up. I think yesterday I didn't get to the last couple examples of the notes, and I did figure out a way to kind of get around my screen sharing woes. Is everyone doing okay? It's Friday. Is it exhausting to sit and watch Zoom all day long and have like not real interaction with people? It's kind of weird. All right, but we get Friday. We have a little break now. Okay, so this is what we were supposed to see yesterday. Nope, that's calculus. Just kidding. Can you guys see this? It says vectors in a plane and it's white. No. Dang it, I did figure out how to do it. Maybe I just shared the wrong thing. Oh, here we go. Now, do you see something that's white that says vectors in a plane? Okay, this was what was supposed to happen yesterday, but I am having some weird issues screen sharing. But it's basically what we went through. We did all this stuff. It was just the last couple examples, I think, that we didn't get to. I think I stopped with force represented by a vector. Did I get to that? Did I get here? I think that might have been where I stopped then. Each class I got in a different spot. That's where I stopped. Okay, so the last couple examples were this representing force as a vector, since force really, those two quantities that a vector has are convenient. Oh, I got one more person. Let me mark them present here. Since those two main quantities of a vector are direction and magnitude, it makes force or makes vectors a really good thing to be represented by a vector. So think like if you had a weight, we have a direction. In general, gravity is going to pull that thing down. And then the magnitude would generally be with what force. So like a kilogram or whatever the force of the weight is. Or if you have, you know, a wheelbarrow that's being pulled, you might have a force pulling it that way or something. And so a direction, and then with what force are you pulling it would be the magnitude. So you guys also saw this probably in pre-cal and maybe even in geometry a little bit. And so those are the last two examples. And I changed this year to pulling, because I always every year have people that are very concerned with why a tugboat would push and not pull. So I changed it to pulling. But say you had these two tugboats pulling on an ocean liner or a big boat. And you have these angles shown there. They're both 20 degrees. And each tugboat's exerting 400 pounds of force. We can kind of figure out what will happen with the ocean liner. With what force will the ocean liner move forward, or in which direction it goes. Because the way I put these boats at the same angle, at the same force, it will make the ocean liner move straight. But obviously, like if we changed one of the angles, it would cause the boat to start going like up there. If we changed one of the forces, it could do the same thing, cause the ocean liner to move in a different direction. But since I made the forces and the angles the same, the ocean liner should move in the direction of this orange arrow here. So we can just turn these all into vectors. We could do this geometrically, right? We basically could take tugboat 1, and then we could move tugboat 2 to be head to tail. And then the ocean liner, that orange arrow, would be that third side. This would be the ocean liner right there. We could do that geometrically. That's kind of how we would have done it in pre-AP geometry when I used to teach that. In this class, I would generally do it as vectors. So we would come up with like a vector for tugboat 1. And the way I usually do that, if I've got information like this, I think of a unit vector that's going at that 20 degrees. So think if we had a unit vector at 20 degrees, well, just think of the unit circle, right? If that was on the unit circle, this coordinate point would be cosine 20, sine 20. So that's a unit vector going at 20 degrees. Our tugboat's going to have a magnitude of 400, not 1. So I just do 400 times that unit vector. That's usually how I would come up with the vectors that I need. If I know a direction and a magnitude, I use the direction to get a unit vector, and it's usually just those, as long as the direction is given as kind of from the positive x-axis counterclockwise, like we're used to looking for, I just use that unit vector, cosine 20, sine 20, or whatever the angle is, and then multiply by the magnitude, and we have 1. The second one would be very similar. We'd have 400. The difference is, remember, it has to be measured counterclockwise. So you'd either want this angle, okay, which would be 360 minus 20, so 340, or you could use negative 20. But it's going to matter that you aren't 20 degrees clockwise. You're going to make sure you want to keep track of where it would be measured from the x-axis counterclockwise. And then that resultant, okay, if we call this the resultant here, the orange thing, the resultant would just be the sum of those two things. So we could add those together. If I find the magnitude, that's the force that the ocean liner is moving forward. If we found the direction, which we could find, it's going to be 0 in this case because it's moving straight across. But we could use that sum to find a vector, and then you find the direction and the magnitude and know what's happening with the ocean liner. Young kids might say, well, it's going to be 800 pounds of force because each of those boats is pulling with 400. But you guys know that since it's pulling at an angle, some of the force, some of the 400 is going that way, but some of it's also going that way, right? Our two components, it's breaking up that 400 pounds that each tugboat is doing, and part of what they're pulling is actually pulling against each other because of the angle. If they were pulling at 0 degrees, then they'd have the full 800. But as that angle changes, part of that force is being lost against them. So we know it's going to be less than 800. Okay, so you guys, that makes sense, right? You guys are good with that? And then the last one has to do with the plane problems that, again, you probably saw a lot in pre-cal. And in general, when you're talking about things like planes or cars or something like that, they aren't going to use mathematical direction, meaning from the x-axis. Planes don't look at the world as being on an x and y axis, right? They look at things like north, south, east, west. So in a lot of like navigation, including probably boats and stuff, you would have a bearing, which usually is the acute angle between the north-south line and where you are. So like if you have this north-south line, if your object is heading this way, we would choose the acute angle between either the north or the south. So in this case, since it's closer to the north, we would choose this angle here. And so say that was 30 degrees. We would say north 30 degrees east, since it's 30 degrees to the east of the north line. Okay, or we might say, if it was down here, and this was 23 degrees, we might say south 23 degrees west, since it's 23 degrees to the west of the south line. So a lot of navigation is given in that way. If that's the case, it'll specify it. Okay, if you're, my computer says my internet connection's unstable, so let me know if you can't hear me or something. But in general, it'll tell you, it'll specify that. If it just gives a degree, that's the mathematical degree, okay, from the positive x-axis. It'll specify a bearing or a north 30 degrees east or something if you're expected to do that. In air navigation, of course, that's even different. It's usually measured from the north clockwise. It's like in air navigation, if your plane is flying this way, it would specify this angle here. Okay, so a little bit confusing, but when mathematicians do things, it's not like the rest of the world decides they're going to do everything just like the mathematicians did it. So math kind of came up with their standard, and other industries, other people came up with kind of theirs too. So those airplane problems, you just kind of do the same thing and you kind of break it down. Just make sure before you try and like plug into formulas we've learned, you need to convert all the directions to that mathematical direction, that angle from the positive x-axis. So we have an airplane here, traveling at a fixed altitude, negligible wind factor, planes going 500 miles per hour. That's our magnitude, with a bearing of 330 degrees. So what they're telling you is this. Plane's going this way. And this is 330 degrees. So when we try to come up with our vector for the plane, we know our magnitude's 500. But if I'm going to use the same thing I did last time, kind of a unit circle unit vector to multiply that 500 by, I need an angle here from the positive x-axis counterclockwise. So I see that first thing is 330. That makes this whole thing 30, right? Because I have to add up to 360. This part over here is 90. So our mathematical direction is 120 degrees. So you kind of have to figure out the angle we want. Okay, and so I can use cosine 120, sine 120 times that 500. That's my unit vector going in that same direction times the magnitude that I want there. So that would be my plane. Those are unit circle values, right? The cosine 120, sine 120. So what is that? Negative 1/2 root 3 over 2. So like we could use those values. In general, you guys can use calculators and things, but you should know unit circle values still. And then we have our wind. That one's given in that northeast. So northeast, it's giving you this angle here for the wind. We want the one between the positive x-axis, which because it's 45 degrees, this actually ends up being 45 degrees as well. But that's the one we want to use. And so for the wind, our magnitude is 70. Our unit vector is cosine 45, sine 45. Okay, and then for the same thing, the resultant is just going to be P plus W. Okay, and if we want the resultant speed, that's the magnitude. So we add P and W and find the magnitude. If we want the direction, we'd then use that same thing to find the direction. Okay, and just make sure you can find direction. Oops. So this is separate. This is just an example. If we have a vector 5, 4, remember that that's giving me, I've gone 5 this way, 4 this way. So we can find direction angle using inverse tangent of 4 over 5, right? Once we have the components, we basically have legs of a right triangle, and we can use arctangent to solve that or find that. Okay, that's the last thing from yesterday's notes. Today, our notes are much shorter, so we should be able to get through that pretty easily. Oops. So let me find the next ones. So today we're just doing vectors in space, which just means what if it's not 2D, what if we've got 3D, and really this kind of applies to even higher order than that. Other than visually, there's not really a lot of visualization of something like 5 dimensions or something like that. We're gonna not really worry about graphing that type of stuff. But otherwise, vectors in space, the reason this one is pretty short is we do mostly all the same stuff. So I'm not going to spend a ton of time on the stuff that we already did. A 3-dimensional coordinate system, I don't know that you guys probably have really seen this since geometry. And even then, it was fairly short. So this is kind of what a 3-dimensional coordinate system looks like. And there's not a standard as to which axis is which. So typically you want to label it. And I'm not great about remembering to do that. In general, what I use is this is the x-axis, this is the y-axis, and this is the z-axis. And so you basically have kind of taken the x and y-axis we're used to, and you've laid it down like on the table, and now what we have is the z going this way. Okay, so in general, that's kind of what our coordinate system will look like. Picture this is kind of flat down on the table, and then the z is the part that's going vertically. Like if you pictured the table being the x and y axis, the z is what's going up and down from there. So we have 3 basic planes in space. Okay, this is the xy plane. This is the one we're most familiar with, right? That's the one we've been working with for, I don't even know, 6 years or something, you guys. All the points in the xy plane have in common something, comma, something, comma, 0, right? Every point in the xy plane has a z value of 0. That next one is the xz plane. There's really no reason that's not a standard. It's just kind of what was chosen by whoever decided to choose it was xy. Xz is just another kind of standard plane that you can graph in, and you could plot functions in and things like that. Like you could do z equals x squared, and that would look a lot like y equals x squared. Right? It would be a parabola in that plane instead. And that has in common, wow, it's loud, something, 0, something, right? All the points in the x plane will have an x coordinate and a z coordinate, and y will always be 0. And then this is the yz plane. And they all have 0, something, something. Right? All points kind of share that in common in each of those planes. Those are kind of our standard planes that a lot of times when we try and visualize a 3-dimensional thing, we'll think about the ways it intersects those planes. And you can then visualize, like, in this plane, it's a parabola. In this plane, it looks like a circle. In this plane, it looks like whatever. And then you can kind of visualize what's happening. So that's one of the ways. Plotting points, not really going to grade your ability to graph in 3 dimensions, but it can be useful. And I mean, you technically should be able to do it. The problem with plotting points is, like, if I say, here's my point, we don't really know where that is, right? Because in 3D, there's infinitely many points between your eye and that point, and then going on behind the computer screen, directly behind that point, there's infinitely many points, right? So we don't really know, like, did I go back and over and up? Did I go forward and up? Did I go back and over and down? How did I get to that point? I don't know where it is in space. So typically you want to, like, label the point or show how you got there. So, like, if we were to plot 2, 3, 5, again, this is, oops, x, y, z. This is the positive. This is negative. So left is, oops, left is negative, right is positive, which should make sense. On the x-axis, forward towards you is positive, and back into the distance, picture this is going backwards, negative. Oops, that's an N. And then up is positive, down is negative. So if we wanted to do 2, 3, 5, we would move 2 in this direction, and then we would kind of estimate 1, 2, 3 in the y direction, and then 5 we would go 1, 2, 3, 4, 5. And so we'd kind of be up here, and you'd picture that that's hanging in front of the screen to the right and up. Okay, and it's like we've kind of smashed it down onto the screen flat. So notice it does not line up with y equals 2 or z equals 5 because of the perspective, okay, that it's now at an angle. It's like we're viewing it at an angle. So it's, even though we've got this here, it's not going to necessarily line up here because of the coming forward or going backwards. So just be careful there. If you're graphing or if you're looking at a graph, generally it's good to either show kind of how you got there or label it. So same with that -4, 2, 6. I would go back 1, 2, 3, 4. 2, I would go to the right 2, 1, 2. And then -6, I would go down 1, 2, 3, 4, 5, 6. Okay, and I'd be over there somewhere. And again, it's not going to line up. Look, it's nowhere near y equals 2 because it went so far back in the distance, the perspective is changing it. So 3D, a lot of people, that's really hard to visualize, see. I'm not going to grade your ability to 3D graph, so don't stress about it. Instead of quadrants, we have octants. We have 4 that are above the quadrants that we're familiar with. So we have like, this would be quadrant 1, quadrant 2, quadrant 3, quadrant 4, right? If this is the positive x, positive y. And then so we have those 4 that are above, and then we would have 4 that are below. I didn't graph all of them. I figured you could figure out what was going on. Then you'd have 4 more octants below. Again, not really worried about you memorizing which one's which and where is what, but just be aware if a problem refers to an octant, they might say the octant like positive x, positive y, positive z or something, in which case you're picturing things being graphed in this octant here, which is probably the most typical. If you're doing an example, is to see stuff in, they might just say this is only in one octant or something like that to try and limit how much you guys have to do. Okay, oops. So formulas, these are again, if you went way back to geometry, we have formulas, finding distance, finding midpoints, things like the formula for a sphere. These are all related to 2D. It's like 2D distance formula. x2 minus x1 squared plus y2 minus y1 squared. Well, in 3D, we take that exact same formula and we just add z's. And it comes from Pythagorean theorem. If we kind of made a right triangle in 2D, this is from Pythagorean theorem. Same thing in 3D. If we're just finding the distance between 2 points, we're basically finding, using Pythagorean theorem to find that. Okay, and sometimes 3D might be called like space, 2D called plane. So they may not say 2D or 3D. If we're in space, we're talking 3D. If we're in a plane, we're talking 2-dimensional. Okay, midpoint, same thing. To find the midpoint, we might not have done this a while. You average the coordinates. Oops, x1 plus x2 divided by 2. y1 plus y2 divided by 2. Okay, in 3D, we do the exact same thing. Which is why this section I don't spend a ton of time. Is it's all the same stuff. You're just adding on z's, basically. Okay, for a sphere, think of our equation for a circle in 2D. It's just finding all points equidistant from a specific point. right? This is how we find a circle. It's finding every point that's a certain distance from a given point, right? We have a center, x naught, y naught, and we're just finding all the points that are r distance away. Notice this is the distance formula, right? These are the same thing, where r would be d in this case on the distance formula. They're the same thing. A circle formula comes from the fact that we're finding all the points that are r units away from x naught, y naught. Well, a sphere is the exact same thing again. We just add on some z's. Okay, so
So will this be a hollow sphere?
what?
So will the sphere be hollow?
It will be hollow, yeah. It's not actually counting the points in between. Yeah, exactly. It's kind of like when we graph a circle, it's really the edge of the circle that we're graphing, not the inside. Yeah. If we did something like less than, then that would get the inside. If we did less than or equal, that would get the outside and the inside, the edge and the inside and stuff like that. Yeah, good question. Okay, so like this is a sphere. From the equation, if it's in this form, it's not always in this form, but if it's in this form, we can get it here by completing the square if it's not already there. But if it's in this form, we know that the center is 5/2, 1, 0. Okay, so we've come like 5/2 out here and 1 over here or whatever, and the center's over here. And then the radius is the square root of 97/4. Okay, or square root of 97/2 if we wanted to at least simplify a little bit. Okay, that would be that sphere that we're looking at. And yeah, it's the outside. And again, graphing in 3D, I can't draw things like spheres very well. It'll look like a circle for me. So I'm not going to really grade that. Okay, with vectors, vectors, same thing as yesterday. You're just adding a z. So our component form from yesterday was this, and now we'll just also have a z component. Our unit vectors were I and j, which they're the same. That's the one in the x direction and the y direction. Now we'll have a k that's also one in the z direction, so that we can write that same, remember this is the same as this. They're just two different forms. We're rewriting them in their unit vector notation, but it's exact same stuff as yesterday, so I don't really feel like we need to spend a ton of time doing that. Okay, addition, magnitude, which was length, unit vectors, scalar multiplication, they're all the exact same in 2D. As in 2D, you just add the component. So like adding works the exact same way. Add the x's, add the y's, add the z's. Find the magnitude. You'll do the square root of x squared plus y squared plus z squared. Unit vectors, you'll take the vector and divide by its magnitude. Sorry. Huh. And then, yeah, it's all the same exact formulas. You'll just add on z's. So I'm not going to go through those. You can go to yesterday's notes and see that. Vectors are parallel if there's a scalar such that one is just a scalar multiple of another. So for example, is 1, 2, 3 parallel to 2, 4, 9? Well, you would just try and think, is there a multiple of 1, 2, 3 that gives me 2, 4, 9? And you might look at that and say, well, if I look at the first one, the multiple would be 2. Well, then make sure 2 times the first one is the second. Well, I go to the next one, 2 times 2 is 4, so that's good. Then I go to the last one, 2 times 3 is not 9. So no. Okay, there is no scalar that will give one to the other. That's all we're looking for parallel, because remember, scalars will give you things that are longer or shorter or going the opposite direction, but they'll be parallel as long as there are scalar multiples. So generally, especially in 3D, 2D you could kind of graph and see. 3D it becomes hard because graphing is hard. So in other words, the vector will have the same direction or the opposite direction, which is what a scalar multiple does. We talked about that yesterday.
Is that a plus sign?
A what?
Or what is like the symbol after the two parallel
Sorry,
signs?
2. That was the
Oh,
word.
two. Okay.
Sorry. Yeah, the word 2. Yeah. Okay, and then that kind of leads to same idea here. If you have points in space and you're trying to figure out if they're collinear, meaning on the same line, that's what collinear means. You could try and graph them, but again, in 3D space, it may go like this and you don't know, are some farther back, some farther forward. It's hard to just look and see. So in general, what I would do, say we had A was 1, 1, 1, and B, oops, that's a B. B was 2, oh my gosh, 2, 0, -1, and C was -2, -1, 0. Okay, this is just a random example here. And we're trying to figure out, are they on the same line? We'll think if they're on the same line, then if I connected these two and I connected these two, they should be on the same line. So one thing we could do is figure out if the vectors in between are parallel. Okay, we don't have slope in the same way that we would in 2D. To figure out, usually we would find slope and that would tell us if they're parallel. 3D, we find a vector and see if the vectors are parallel. So we're gonna find vector AB. Okay, say we had A, B, C. I didn't really plot them in the right place, but I just put them on there randomly. So say we're trying to find AB and then BC and try and figure out if they're parallel. If they're on the same line, they have to be. So remember from yesterday, all we do to find AB is we take the terminal point minus the initial point. Okay, find the distance we moved in the x direction. It's 2 minus 1 is 1. In the y direction, it's going to be 0 minus 1. So we went left 1 or whatever. And then the z direction, it's going to be -1 minus 1, so -2. Okay, and then we're going to find the vector BC. And do the same thing. So I subtract my x's, the terminal minus the initial is going to be -4, and then -1, and then 1. And so my first question would be, are AB and BC parallel? And so I would just think, as there are multiple, and I just kind of go down, to get the x's to be a multiple, I would multiply AB by a -4 to get that 1 to become a -4. But notice the y's don't have that same multiple. So no. Oops. There's no C such that C times AB equals BC. Okay, or if you want to choose a different letter, so 2 C's or whatever. There's no constant multiple that will give you one vector to the other, which means the points are not collinear, right? If they were parallel, you kind of need to think, why is that enough to know they're on the same line, right? How do we know they're not doing this if they're parallel? Well, notice the way we picked it, they share a point. So not only are they parallel to each other, they also both share the point B, which means they can't be doing this. They must be doing this. Okay, so in this case, normally parallel doesn't mean the same line. Parallel means parallel, but because they're parallel and both going through B, we know they must be on the same line. So this would be enough for us to know, like, if 3D things were parallel. So there's a lot of geometry stuff, but it is stuff that will kind of apply to what we're doing. And that's basically all that there is for this. Does anybody have any questions? Okay, then, oops, I will post the video. So if you guys need to go back to anything, you can. At this point, we've done 2 of the 3 lessons that are on your problem set that's due next Friday. So you got plenty of time, but I would get started if you have a chance. Because again, if you leave it all till Thursday night, it's a lot. It's meant to kind of be done a little here, a little there. It's meant to be basically 3 nights of homework. So keep that in mind. But otherwise, we are done. If you guys don't have anything you need, then you guys can go.
Wait, you'll post yesterday's, right? Did you post yesterday's already?
I haven't posted yesterday's. I'm going to post it today with this one. I messed up and didn't post it yesterday, but I'll post the notes. Yeah.
Okie dokie. Thanks.
All right. You guys have a good afternoon and a good weekend.
Thank you.
Thank you.
Mr. Smith.
Bye.
Bye, all.
Bye. Thanks.
Mr. Smith, thank you.
Bye. Have a good weekend.
Can I ask you a quick question?
You can.
It might be kind of stupid, but yesterday we talked about like joining, like adding vectors, but then we like did this proof, or I don't think we did the proof, but it's like adding the 2 magnitudes.
Oh, yeah. Like the magnitude of x plus y and then the magnitude plus the magnitude of y.
Yeah.
Uh-huh.
I was wondering how, like, could you just like retell me how to actually find the magnitude of x plus y?
Yeah. So,
Like, x plus y is in the middle, I guess.
I'm going to share a screen real quick so I can write on something. I'll just go back to what I was doing before. Whoa. Scary. I'm outside and it's like a... Oh.
Or is it the thing where it's like the magnitude is like the Pythagorean theorem almost, but do you just like add the points together?
Yeah,
So it's
can you see the screen again? Sorry. So
you're
say we have x and y. This would be x plus y. Like the single vector plus y. Oh my gosh, I thought it would stop soon. So normally to find the magnitude of x plus y, I'm clearly gonna have to move, I guess. We would literally take those vectors, add them together, get the single vector, and use Pythagorean theorem on that. So like this vector also has like an x and a y distance,
okay.
and so you'd use Pythagorean theorem. So like if x was, say x was 2, 3, and y was 5, 7, x plus y would be 7, 10. And so the magnitude of that would be the square root of 4900.
Got it. Okay, that makes sense. And you can also do it like without finding the resultant vector. You can like do the components and do like the x, like the first component of the x and the y squared plus the second component of the x and the y squared. Right? All right, cool.
Say that one more time, sorry.
Yeah, I can show it. Is that easier if I draw it out?
Okay.
Let me draw it out. Is it like this?
Yeah.
Okay, perfect. Thank you.
Sorry about the noise. Yeah, that's it. All right.
Have a good weekend.
You too.
I had a question about the slides. If you could screen share again, please.
Yeah.
That
is
was
insane.
the one with the 8 octaves.
Jeez Louise. Okay, there's my slides again. Woo.
Okay. It was the one with the 8 octaves.
Okay. It's towards the top, I think. I think it was after this. It's weird it doesn't load right away. Oh, here it is. Okay.
Okay, there it is.
The label-
Yeah, would these be graphed at a different perspective than what we did earlier?
I did graph them in a different perspective. Yeah, right now, because I wanted to turn it to be more like we normally see the quadrants. So I tilted it. But yeah, this is the positive X and the positive Y on these ones. I kind of just
Okay.
turned the graph so that it would line up more with where we're used to seeing. Quadrant 1 is the positive X, positive Y. Quadrant 2 is negative X, positive Y, and so on. So I kind of tilted it a little bit. Yeah.
Okay. And
Yeah.
so when we graph it, do we always label our axes to make sure that we
You technically can graph any way that you really want. I would just make sure you label the axes. So like here, I would label this like X, Y, Z so that it's obvious. Because technically you can graph with the Z over here or the X over here or the Y up here if you want to. Typically that's not where you would put it. But like if you use, what's it called? There's Google SketchUp or programs like that. You can model things in 3D. They make the Y-axis. They put the Y-axis here. And a friend of mine was trying to get help because they're like, why is this graphing weird? Which are these or which axis? And I, thinking like math, I was like, oh, well, this is X and this is Y and this is Z. And they graphed it and it would always graph like sideways because for them, the standard was that they put the Y up here. So it's not that you can't graph other ways. Generally, you want to label the axes just so you know which is which. And like in the program I use, these bold arrowheads, those are the positive ones. It automatically puts those there. But yeah, generally, I would say this is kind of its typical way of doing it. But you can actually do it other ways. Just label the axes. Usually they're labeled or I'll label them. But if I don't, you can always ask.
Okay. And so so it's like the general way to do it, it's like you put the arrow wherever the positive end is and then leave the other side like just like a line.
No, I mean, there's usually going to be arrows on all of them. The program I use happens to do that, but I think normally there's going to be arrows on all of them. This one they cut off here, but they should be here. The picture cut them off.
Yeah, there's one on the X.
Yeah, the X has both of them, but they should be on all of them. I don't know how I would say generally, and I didn't do this very well. Generally, where you put the X, the Y, and the Z, I would say is probably usually the positive side. It's like if you label them here, I would say X, Y, and Z, and that indicates that this is positive, positive, positive. But again, that's not necessarily a standard. It can change.
All right, that's cool. That's all I had.
Okay. Well, have a good
All
weekend.
right, thank you.
Uh-huh.
You too.
Bye.